Good afternoon and welcome everybody to the Stony Brook University College of Arts and Sciences preview session. I'm Amanda Mills, Assistant Director of Admissions for Stony Brook. I have a few housekeeping notes before we begin. First, please use the Q&A feature to ask our speaker any questions and we will answer them at the end of the presentation. Second, note that this session is being recorded and will be available on the admissions YouTube page soon. And lastly, there are a variety of topics that will be covered during the next few weeks as part of the College of Arts and Sciences preview series. And we encourage you to join us for any that interest you. Now, please join me in welcoming Stanislaus Wong, SUNY Distinguished Professor of Chemistry, who will present Living in a Material World. Professor Wong?
Okay, thank you, Amanda. I appreciate this. So what I will do is I will share my screen and describe a little bit about what I mean by my title and topic. So in my research group, we actually study materials chemistry quite a bit. And what I'm going to be describing is maybe not so much a course that you might be taking during your first year, but that you might encounter over the course of your undergraduate career at Stony Brook. So what do I mean? So one of the courses which I teach is actually course 518, 378, and the 3 is something which is related to the undergraduates and their curriculum, and it's materials chemistry. And this course, which I'm involved with, introduces chemical concepts to design, select, and deploy materials in technological applications. And so we address things such as how to structure at the atomic, molecular, and supramolecular level affect properties for given application. How do the desired properties end up driving the choice of material that we end up synthesizing? And so some of the objectives of the course that I teach, and you'll find this for every single university course that you end up taking, is a set of outcomes, or what we hope that you gain by taking our course. And so in this particular case, we are hopefully going to be able to go through materials chem lit searches, looking at lengths and time scales relevant to the chemistry of materials, structural characteristics and properties, how we make materials, modes for characterizing materials, as well as structure property correlations for different classes of materials. So, and again, I just want to give you a flavor for the sort of things that we talk about in my class, and I'll be glad to answer questions about them afterwards. So the first thing you may want to ask yourselves is, what is a material? And so a material is broadly defined as a solid state component or device that can be used to address a current or societal need. And so essentially materials chemistry is focused on understanding the relationships between arrangements of atoms, ions, or molecules, and their overall properties. And the broad field in which I have been involved with for many years involves studying structures, synthesizing and characterizing materials, and using techniques to be able to predict the structures and properties so we can design things that are going to be of practical interest to everyday life. So one of the things that we think of materials from a historical perspective is that materials are intrinsically connected to culture, and advances in society are going to be dependent on the availability of materials and their use. And really, if we go through the historical context, whether we're going from the Stone Age to the Bronze Age or the Iron Age, etc., every historical period tends to be associated with the predominant use of a material or the reliance on a specific material, whether it be bronze or iron or what have you. And so that usually defines the socio-political, economic, the military, dynamics of any given age. And so, right now we are in the information age. And essentially, when we talk about materials, if we start out from the very beginning, we think of deriving, or we think of being motivated by nature. And so what we would want to do as scientists is to develop techniques that can produce materials with superior qualities in order to mimic and potentially bypass nature. So the selection of materials becomes a really important goal. And so if you think about, what nature has done over the years, and you think that essentially they have had billions of years in advance of us in terms of being able to design a reasonably effective and efficient classes of structures, we can go anywhere from wool, from polypeptides, from silk, etc. And we can migrate over to things like resins and shellac, which was used as a coating for many of these statues and ceramics and so on and so forth, art forms that were developed in ancient times, moving on to rubber, which is isolated from trees, Hevea brasiliensis, and over to wood. And the main important component of wood includes things like cellulose, cotton, wood, and other plant fibers, which has been essentially known to humankind for thousands of years, but it's really highly insoluble and difficult to process. So if we think about from a chemist or a scientific point of view, what we would want to do is to take things that are naturally occurring and to chemically modify them. And for instance, one strategy might be to react it with nitric acid. So essentially taking the basis, the backbone of cellulose, reacting it with acid, and creating these different groups on them, which is what chemists fundamentally do. We would like to chemically design, we would like to manipulate at the molecular scale different sorts of structures in order to introduce functionality with the purpose of making them usable, making them useful. And so if you do this, you can make things, as you can see, other scientists have done, over the years in the early stages of working with cellulose, everywhere from colloidin to celluloid to rayon, and even to billiard balls, right? So there are many different reasons why being able to use chemistry in a practical and rational, tunable way will give you something that is going to be worthwhile from an industrial as well as from a practical point of view. So one of the things that we think about as a chemist, materials chemist, is how do we make things like billiard balls, all right? And so you can envision it as a top-down route where we go from wood and we go to paper products or golf covers, etc., or the bottom-up route, which is a way of being able to take molecules and to create plastics and vinyl, etc. And then you can create, for instance, these different products, automotive interiors, etc., through polymerization processes involving simple starting materials, simple chemical units. Okay, so the whole idea of being able to use materials chemistry is that we want to design materials that will yield in-service performance, durability, and effectiveness that's going to be quite worthwhile and desirable. At the same time, these materials need to be relatively simple to make. They need to have good quality control, and they need to be, in essence, relatively cheap to make, cheap and easy to dispose of and recycle. So there's a balancing act among these various considerations. And in practice, all of you, believe it or not, make a number of different material choices. So for instance, if you were to buy Coca-Cola, you could get them in aluminum cans or glass or plastic and so on and so forth. So even such a thing as Coke comes in these different packaging possibilities, each of which has various advantages and disadvantages as well. So when we're thinking about materials, and you think about, for instance, Coke in these various types of manifestations, whether it's, again, cans or glass bottles or plastic bottles, containers, what you're trying to fundamentally worry about is the choice or the selection of a material. We need to consider this as corners of this trigonal pyramid, right? Where we have the structure of the material that we want to look at, the arrangement of atoms at the atomic, microscopic, macroscopic level, the properties that these arrangements of atoms give to us, how they respond to external stimulus, what their mechanical, electrical, thermal, magnetic, optical properties tend to be, how we process them, how we make them in the first place, how they perform in a different application. So in the previous application, it's storing Coke. And then this whole idea of being able to get these different sorts of information occurs through structural characterization tools. So these are all interconnected problems, interconnected qualities, interconnected issues that really take up a lot of the time of basic scientists as well as engineers. All right. And so when you come into a university setting, you're going to basically be looking at the sort of questions, the sort of issues that underlie the problems that I'm outlining in this particular slide. And so one of the things that underscores all of these issues fundamentally are scales, right? So what I'm showing you here first and foremost is a scale in terms of size. So when we go from an ant, which is about 5 millimeters, to a dust mite, 200 microns, fly ash, 10 to 20 microns, all the way to DNA, ATP synthase, or DNA in atoms of silicon, which tend to be in a nanometer scale range. We're going all the ways from centimeters, all the way 10 to the minus 2 meters, all the way down to the nanoscale world, which is 10 to the minus 10 meters and 10 to the minus 9 meters. So this scale that you were looking at is really a large domain that spans a lot of different types of phenomena. And this is what, again, the natural world has been able to provide over the millennia and billions of years. And what we have essentially to mimic, to respond to that, is, for instance, head of a pin, which is about 1 to 2 millimeters. X-ray lens is 35 nanometers, nanotube electrodes, again, tens of nanometers, carbon nanotubes, which is what I work with in my group, amongst other things, which are about 1.3 times 10 to the minus 9 meters, quantum corrals, which involve being able to position atoms, say, around this particular ring, and this is about 14 nanometers in terms of diameter. So what you see is that we have a range of different sizes that sort of span the same scales that nature has been able to provide. And what we hope to do is to design materials that will behave just as well as, if not better, than what nature has already given to us. And so, as you can see, it's really not, it's no small feat. It's quite hard to basically do. So what are the important reference lengths that we need to be aware of? Atomic radii. For instance, if you study atoms in chemistry, as you most likely will, in general chem, we introduce you to things like carbon or iron atoms or cesium or gold atoms, which are about 0.1 to 0.3 nanometers, so 10 to the minus 9 meters. That's very, very small. Bond lengths, hydrogen, hydrogen, carbon, 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 silicon, silicon, iodine, iodine. So most of these bonds are, again, very important for biochemical processes. They keep us alive. And so these bond lengths, 0.1 to 0.3 nanometers, C60, 1 nanometer, again, single wall carbon nanotubes, a matter of a material of research interest in my group for many years, 1.4 nanometers. And just as a comparison, influenza viruses are 130 nanometers, E. coli about 3 times 0.6 microns, and red blood cells are 8 microns. And so the idea of scalability is quite important, quite crucial. And why do I say that? Because if, for instance, you look at features on a computer chip, what you figure out is that when you go from about 10,000 or 10 million rather nanometers, which is what the sizes of these particular chips were back in 1971, all the way down to the present day at almost the atom scale, you're basically spanning a wide range of dimensions. And I remember basically having a Commodore 64, where 64K was considered to be a state of the art. Right now, if you don't have, essentially these Intel Core i9, i10, et cetera, you're not getting anywhere. And so what we're figuring out is that the number of transistors which are being incorporated into these microchips is getting, really, really, exponentially higher with every single generation. So the computers are becoming more and more powerful with each generation, which is as it should be. But that means you're scaling down the capabilities of these various computer devices to get down to that level. And the only way you do this is making advances in materials science and chemistry, which is exactly, again, why my group is, amongst others, very excited about working in this field. So again, as you can see, even in the past, couple of decades, going from silicon all the way down to the field effect transistors that are in operation now, you are again really shrinking down the amount of, the size of the laptops, the size of computers, but at the same time making them more and more powerful. Well, that's no accident. It's because of advances in understanding how materials are behaving, how chemicals and chemical bonds are joining to each other, and how that interaction is giving you a functional device that's showing you and evincing really high performance metrics. Okay, so I've talked about the fact that as we go from bulk to microscopic to atomic and subatomic scale, these differences matter. And in fact, what is really, of great highlight, especially in my group, is that when we look at things at the very small scale, the nanometer scale, the properties of these materials will also change dramatically. So in other words, if you're trying to optimize structure, processing properties, performance, going down to the nanometer scale is one effective route of being able to achieve all of that simultaneously. Okay, so time scales, I've talked about, size scales. Time scales are going to be very relevant for chemistry. So for instance, things like, vibration, radical chemistry, the atmospheric chemistry, ozone chemistry, the soot chemistry, etc. Thermal chemistry, all of these occur over different scales, ranging from, say, picoseconds, nanoseconds, microseconds, milliseconds, as well as seconds. So most of the phenomena that we are, I guess, comfortable with happens at a scale which is in the seconds, but in many respects, many of the most important processes happen at these much faster scales, which require correspondingly more sophisticated tools in order to understand how these things operate and work. Okay, so energy also couples with this as well. So I've spoken a little bit about length. I've spoken about time. If you were to study physics a lot, you know that energy also will become a part of this equation as well. And what we're seeing here in this slide is that if we consider this multi-dimensional sort of paradigm where you have, for instance, cosmology dealing in 10 to the 10 years, 10 to the 26 meters, solar systems slightly less in terms of scale, all the way down to string theory, which is 10 to the minus 32 centimeters, 10 to the 18 giga electron volts. These are spans vast amounts of energy. So these are very, very high energy processes at very, very small time scales, whereas these are very, very large. Cosmology tends to be very, very large distances at very high time scales as well. And most of what we do in terms of chemistry and physics is somewhere in the middle of all of this. But again, the purpose of the slide is just to show you that all of these things are going to be important, going to be crucial. We need to worry about the context, the background, where we are in terms of the energy scale, the time scale, as well as the length scale. All right. And so, again, if we consider everything that impacts you in what you do in your everyday life, all of these things become important because they're all interconnected. They all interrelate to each other, right? So essentially, the visible light, is important for light bulbs, night vision, suntan, dental curing, fiber optic technology, et cetera, bioimaging, more in a terahertz region. Microwave tends to be where radar, microwave ovens work. Broadless and wireless occur, AM, FM radios in the megahertz region. And then if we go down to the more higher energy type of phenomena, X-rays, baggage screening, crystallography, PET imaging, medical imaging, cosmic X-ray, astronomy, all of that. That's again in the much higher energy range and scale. And so, you know, all of these things that we're looking at are also going to be dependent on energy scales that also are a function of the size of the phenomenon that's undergoing these sorts of phenomena. So whether it be a baseball, whether it be bacteria, water molecules, subatomic particles, all these are going to act differently. And I think that what this particular slide really highlights is really the interconnectedness between all of these references, whether you're dealing with energy, whether you're dealing with size, and scales and time scales and length scales. All right. So if we take again this whole context of energy, length, and time, and we apply them to material science, and just again to go back to what I spoke about earlier, if we consider all of these considerations and points, what are some practical materials that are going to exist in the universe that we are going to be most comfortable with in terms of analyzing and studying? Well, number one, they're going to be metals, which are strong and ductile. They have high thermal electrical conductivity. They're going to be optically opaque and reflective. You have polymers and plastics, where we have things like covalent bonding, which essentially means a sharing of electrons. And the very fact of that means that the polymers and plastics are going to be soft and ductile, low strength, low density. And these include things like thermal and electrical insulators. They can be optically translucent and optically transparent as well. And then you have ceramics, which are, say, ionic bondings. You have compounds of metal and non-metallic elements, oxides, carbides, nitrides, sulfides, etc. Now, the fact that you probably don't recognize most of these terms, don't worry about them. What you need to understand fundamentally is that these are various different classes. You've heard of metals, you've most likely heard of polymers, you've heard of ceramics. So things like, metals like copper wires, polymers like the containers that, the plastic containers that carry your beverage, ceramics, for instance, for cookingware, and the tiles on space shuttles and other space vehicles, etc. All of these have different properties, different functions. And what this slide really highlights to you is that the nature of the chemical bonding within metals, within polymers, within plastics or ceramics really dictates, it determines why you see the properties that we so value, that we so find attractive in each of these classes of materials. So it's not an accident that metals have high thermal electrical conductivity. It's not an accident that some polymers are optically translucent or that some ceramics tend to be non-conducting. So as an example, the whole principle here is that by using chemistry, by designing chemistry, you can actually target various types of applications that you have in mind. So for instance, you don't coat a space vehicle with the same sort of plastic that you would use to store Coke in. All right, it's just not the same, right? You need to have a very different, specific targeted application, which is why you need to understand how all of these things work and operate. So again, these are examples of why chemistry is in fact the central science, why it underlies how materials are basically formed and how they are relevant for a whole host of applications. You can't fly, there's no electricity, all right? You can't build skyscrapers without metals, all right? You need ceramics, you need for Pyrex containers, you need polymers to be able to make cars, clothing, plastic containers, etc. And so these, again, have different sorts of properties, whether it be conductors, whether it be heat resistant materials, whether it be polymers, which are things which can make, for high durability and flexibility simultaneously. Okay, so essentially some more types of materials that people analyze: biomaterials, semiconductors, composites. So biomaterials are used in hip replacement medical technology, semiconductors, the Pentium chip as an example, and composites, fiberglass surfboards. Each of these, in effect, are more complex types of architectures that incorporate things like metal, ceramics, polymers in a hierarchical architecture that's more sophisticated, but in a way incorporates the functions of these individual subunits into something where the whole is greater than the individual parts. All right, so that's where, again, having these sorts of really high performing functional composites are really going to be crucial for being able to get these more high performing structures. Okay, so in essence, materials chemistry is involved with picking an application, determining the required properties, whether it's mechanical, electrical, thermal, magnetic, optical, and how it lasts in the environment, and identifying the properties that you wish to highlight, identifying the candidate materials, and correlating both physical structure and chemical composition, and being able to identify the required processing. So for instance, processing is about synthetic protocols that we're able to generate. So whether it's changing structure, overall shape, casting, sintering, vapor deposition, doping, etc., all of these techniques are useful in being able to design the material that you end up wishing to fabricate. So in essence, when you're going in as an undergraduate, when you're coming to Stony Brook, what you're going to be to analyzing are the nature of the atoms and the bonds that underlie the properties that are observable, and being able to understand the nature of physical structure and chemical composition that underlie the materials that I've just highlighted to you in these previous slides. And in the process, when you're able to do all of that, then really understanding the methods of being able to make the material. So it's really a multifaceted, transformational sort of set of courses that really allow you to give you perspective. It gives you the whole picture of what it is that goes into making the material that you take for granted when you look at every single day. You're looking at your computer or a cell phone or a smart device. Well, guess what? That's made of many different, thousands of different components that have been put together in a rationally thought out way. And it's functioning in a way that, you know, many of you may not understand the nature of the complexity, but being able to pick out, to understand how the bonds translate into something which is, you know, ever more sophisticated, the primary, secondary, tertiary levels of understanding that goes from the atoms and molecules all the way to your cell phones and smartphones. That's what it is that you can envision, that what chemistry allows you to basically do. Okay, so any questions at the moment before I actually get to an example of what I sort of do in my own lab that hopefully is inspired by the sort of ideas that I've been talking about at the moment. All right, so again, if you have any questions at the moment, please feel free to ask. And if not, you know, we can certainly, you know, talk about them at the very end. Okay, so again, these are the whole principle, the whole strategy of how you would go about thinking of materials in a thoughtful and precise manner to really pick out, you know, what sort of materials that you would like to generate. And so one of the things that we do in my group is actually to look at nanomaterials and a very specific purpose for the energy crisis and energy consumption. So as all of you know, gas prices are really, really high, but in part is because the demand for energy is really, really high as well. And so the point of it is that fossil fuel reserves will be rapidly depleted at some point in the future. And so to be able to develop and exploit alternative renewable energy resources requires different solutions. And so my group actually looks at a very specific class of materials called nanomaterials. And so I actually hinted at what the advantages of nano. These are materials that are characteristic of sizes that are, say, 10 to the minus 9 meters, the nanometer scale. All right, so these are very, very small. You can't see them with your naked eye. You need fancy microscopes to be able to look at them. But the advantages of doing this is that the materials that my group works with have very high surface areas, very high unique surface energy, surface chemistry that can allow us to influence the nature of thermodynamics on different sorts of reactions. And the small dimensions that we have within these materials allow for favorable mass, heat, and charge transfer. So my group looks at things related to electrodes, batteries, hydrogen storage. And the one thing I want to talk to you today a little bit more about is actually fuel cells, all right? So we are trying to design nanomaterials that are going to be very, very helpful, useful for fuel cells, amongst other things, all right? So what do I mean by that? A fuel cell, okay, converts chemical energy from a fuel like hydrogen into electricity through a chemical reaction using an oxidizing agent. And so one of the most important typical ones is the proton exchange membrane fuel cells. But there are many variations of this. There's a direct methanol, direct ethanol, direct formic acid fuel cell. So you've heard of being able to use, for instance, crops for ethanol fuel, for instance. So, ethanol, all these alcohols are basically useful to drive fuel cells, all right? And so essentially, and again, you may not understand the terminology, what I'm talking about here, but the bottom line here is that you have reactions that take place within the fuel cell at the anode and the cathode, and the overall reaction that this particular fuel cell is involved with is hydrogen gas plus oxygen gas becoming water. Now, the problem is that these things don't just happen spontaneously, all right? You need a catalyst to drive the reaction in order for it to occur. And one of the things that drives this reaction is actually platinum, which unfortunately is actually very costly and needs to be either optimized or replaced for a number of different reasons. Now, a direct methanol fuel cell, as I've spoken about, one of these things, it's based on methanol, but the overall reaction here for a direct methanol fuel cell, methanol plus oxygen going to CO2 plus water. And so at the anode, where you essentially have this oxidation process, you have methanol oxidation taking place, methanol plus water, catalyzed by platinum ruthenium, going to acid plus CO2 plus six electrons. And at the cathode, you have an oxygen reduction reaction. Oxygen plus 6H plus 6 electrons catalyzed by platinum going into water. Now, again, these processes, which are critical to the proper functioning of this overall fuel cell, requires the nature of using these catalysts, platinum ruthenium or platinum. Now, the problem with platinum is that it's extremely expensive, all right? $1,100 per ounce. And so one of the things that my group, amongst many others, would like to do is to replace platinum with things like nickel or copper or iron, and which are actually much cheaper. So there's a much difference between platinum, which is about $1,100 per ounce, versus nickel, which is $8 per pound. All right, so that's a very, very big difference. Or iron, which is $170 per ton. All right, and so the other thing about platinum, which isn't so great, is that platinum decomposes, it dissolves, it passivates, it does things which makes the catalyst not very active. So it's not very good, all right? So that's one of the reasons why, as a research group, we want to replace platinum. So again, getting back to the materials chemistry part that I spoke about much earlier, how do we design materials that will give you equal bang for the buck, but it's going to be much cheaper, much more environmentally friendly, much more abundant, much less scarce, okay, much less expensive than things like platinum. And so one of the things that my group was interested in looking at, and we published this over 10 years ago, was the idea of looking at nanowires of metals as a new paradigm, an architectural paradigm, a model system for direct methanol fuel cells. And so these wires that we design in my group show both enhanced activity and enhanced stability. And again, the what you see on your left-hand side shows us that you have low energy crystalline planes, good movement of electrons, good surface properties, and they're stable simultaneously. There's not as many defects. They don't dissolve and they don't oxidize. They don't degrade. They don't break apart quite as easily as your standard platinum nanoparticles. And so if you look at a picture of some of the wires that we make on the left-hand side versus the particles that are commercially available on the right-hand side, our wires, even from a glance, are going to be, have fewer defect sites, more chemically homogeneous, structurally monodispersed. They're going to weaken the interaction with oxygen and prevent passivation of catalysts. So it's a much more highly active structure that you see for the palladium nanowires, which is on that left-hand side. Okay, so here's the other thing which we also should be aware of. So it's not only the chemical composition which matters, the fact that you make these wires. What I'm also showing you here is something which I also mentioned earlier, is that the morphology, the architecture will also be crucial. So whether I'm looking at a so-called 0D, which is a round particle, versus a 1D, which basically means a long wire like material, makes that the 1D wire is going to behave better than a 0D spherical particle. And as I've kept highlighting and emphasizing over and over again, when I go down to a really, really small scale, even for something like a nanowire, where I'm going down to 2 nanometers, and you don't have to really know what a surface area or mass activity really means, but from a bar graph, you can tell that the smaller the wires that I'm able to make, the higher activity compared to the commercial platinum particles that are available and that are commonly used. So there's a relationship, there's a correlation, there's a connection between not only the morphology, the architecture, but also the size of what we generate relative to, say, the commercial platinum that's commonly used in these various sorts of systems. All right. So what my group does fundamentally, first and foremost, is that what we're going to do is we're going to take, say, some of these platinum gold nanowires. We're going to tune the chemical composition of these wires, and we're going to, at the same time, make them really small and make them into wires. So because we know that the 2 nanometer wires behave really prominently compared to, say, some of the larger wires, and the 1D structures behave better than the 0D particles. The combination of all of these means that if we couple control over chemical composition with a 1D architecture, we can lower the noble metal loading, in other words, lower cost of nickel, copper, and iron, and then we get better durability and stability in terms of the overall architecture that we're able to generate at the very end of the story. So in other words, that what we're trying to do in my lab is to control materials chemistry so that we're tuning both chemical composition, structure, architecture at the same time, and simultaneously, we are going to minimize the amount of platinum with things like nickel, copper, and iron. And one more, architectural sort of variant that we study in my group is we actually take a core of palladium or metal-based alloy cores, and we actually coat this with a platinum monolayer shell in sort of a motivating motif that was inspired by work that we did with Radko Adzic at Brookhaven National Lab. And one thing I should mention is that one of the advantages of coming to Stony Brook is that you're very close to Brookhaven National Laboratory. And Brookhaven National Laboratory represents one of the few Department of Energy laboratories that are actually in the Northeast, all right? And so this is a major user facility, and many students, undergraduate and graduate students, have the opportunity of actually working at Brookhaven National Lab. That's a big plus when you come over to Stony Brook. So the point here that I'm actually showing you is that we are trying to be sophisticated and nuanced in how we design our architecture so that we're able to take advantage of not only the fact that we're able to control the chemical composition of the inner core atoms, but also this outer platinum shell. And having this platinum shell means that you minimize the amount of platinum that you're using for catalysis, while simultaneously applying what is known as a compression strain and ligand effect, thereby essentially tuning the platinum to make it really active for oxygen, OR activity, for the oxygen reduction reaction, which I talked about much earlier. And again, this is actually my last slide because I wanted to really have a lot of time for questions. But what you can see here is that if you're really careful about how you're approaching the chemistry part of it, you can design materials, as I'm showing you right here, where in going from ever higher levels of chemical and physical sophistication, you're developing motifs that are going to be considerably better than what is available for commercial platinum. So commercial platinum is right here. We make elemental palladium nanowires and homogeneous alloyed palladium 9 gold, core shell platinum palladium, and finally platinum palladium gold nanowires coated by platinum. And as you go every step of the way, you can design chemically using material chemistry principles. You can tune and tailor performance values that are going to be considerably higher than what you are getting commercially. And so what my group does fundamentally is to make materials that are hopefully going to become the backbone of technologies 20, 30, 50 years into the future. Because as you can see, even at the lab scale, all our structures outperform everything that would normally be happening on a commercial platinum scale, commercial platinum nanoparticles. Again, even at this sort of study, which we actually did about 10 years ago. So being able to tune chemical composition and structure allows us to basically tune that level of activity. Okay, and so with that, let me just thank you for your attention. And again, I wanted to leave plenty of time for questions, and I'm happy to answer questions about Stony Brook itself, the undergraduate program, etc. And with that, I'm going to pass it back to Amanda.
Hi, everybody. As I put in the chat earlier, if you do have questions, you can either raise your hand and I'll unmute you to speak and you can ask your question, or you can use the Q&A icon to post your question if you'd prefer to do that. We'll give everyone a few minutes to, if you do have any questions, and we'll check the Q&A. Let's see.
I'm actually going back to the beginning so that you have, I try to cover a number of different examples, but hopefully again, it gives you some idea of the usefulness of what chemistry is about fundamentally, and how it impacts how you're living in this in the world and the universe.
So we have some questions coming in. The first one is, what has been a recent breakthrough in material chemistry, or any recent?
Okay, that's a really good question. It depends on the field. I think that one of the things that people have been able to design and still are trying to design are room temperature superconductors. So what that means is that to create materials whereby you don't have any level of, I guess, you don't have any loss of conduction at room temperature, and that means that you can almost have a limitless supply. You can solve the energy problem very much in that way. The other thing which I would also mention, I really haven't gone into, are some of the questions or some of the research that people have done with respect to designing new batteries, understanding how batteries are basically created and formed, and being able to tune for that. So there's actually a lot of work which is being done in being able to design better anodes and cathodes and electrolytes for lithium-ion batteries. Another point, as I mentioned, about fuel cells. And one of the things which I didn't really highlight too much is that in this presentation was the characterization part of it. So one of the things which has become a really major question for what scientists are trying to do is to understand how materials are behaving as they are functioning and performing. So for instance, in your car, as the battery is running, what in fact is happening to the battery material itself? Is it degrading? Is it forming dendrites? Is it actually somehow breaking apart? As you have heard, one of the problems with batteries is that they actually catch fire under very, inconvenient or sort of unfortunate circumstances. And one of the things that people want to do is to mitigate, avoid that. And one of the things that people have been trying to do is, again, to create, better battery materials that don't catch fire, and actually cheaper things, alternatives as well. And as I mentioned, one of the things that are really relevant for fuel cells is to, for instance, replace platinum with iron, nickel, and copper-based, as examples, catalysts, and to do this on a large scale, so that again, one of the things that you probably are, and even for the catalytic converters in your car, which is actually catalyzes other reactions which I haven't gone into, but catalytic converters in your cars tends to use things, again, like platinum, ruthenium, things like this, which are very, very expensive. So people can design other catalysts that incorporate much more plentiful and cheaper elements, then that again will be a very positive thing. So there's many different elements that or things that people have been trying to study, and hopefully that sort of gives you a flavor for that.
Thank you. And our next question is, what are some of the materials biochemistry students can work with and study at Stony Brook?
Okay, so that's a very good question. Again, what I would say is, and I'm actually not trained in biochemistry, so some of my other biochemical colleagues would be able to answer that question much more precisely than I can. But one thing that you will study are how red blood cells operate, how enzymes operate, how DNA is constructed, etc. And just to give you sort of a feel for how some of the issues of biology and biochem, say for instance, enter into my own research. We've actually looked at toxicity of nanoparticles in different marine and cell environments. We've actually developed carbon nanotube-based drug delivery vehicles where we actually put and joined onto different biochemically active molecules onto the outer edges of carbon nanotubes and use these as a marker as well as a targeting mechanism to get into tumor cells that were subsequently destroyed when we activated the tumor targeting agent after these nanotubes had transported the drugs into the tumor cell. So there's many different mechanisms whereby you could get involved with research. And again, really biochemically intensive studies. There's many colleagues whom I have both in the chemistry department as well as biochem, molecular cellular biology, and BSB, structural biology. They will certainly do a lot of that sort of work in being able to understand fundamentals. And again, what my group is interested fundamentally at the end of the day would be to not only create, tune, and tailor these sorts of materials, but actually use them within biologically relevant contexts and applications. For instance, drug delivery, or maybe imaging, or other types of sensing would be something else we have worked in the past as well. Okay, you're muted, Amanda.
That was the last question in the Q&A. If anyone has any final questions or wants to raise their hand with any questions, still have time to do that.
Any questions about admissions or any questions about, I guess, classes sort of thing?
A question we do get a lot is, in terms of undergraduate students, first year, second year, third year, when are students likely to be able at the undergraduate level to actually participate in, resume building experiences, whether that's research or internships or teaching assistantships?
So I guess freshman and sophomore, I get it depends on the PI, and one could, if I were you, interact with the faculty member in question to ask if he or she has a position in their lab in order for you to do work in that you're interested in. I myself have recently taken in freshmen and sophomore, et cetera, to start to understand how to use and the chemistry principles that I've talked about to design, again, some of these materials for fuel cells and batteries and biological applications. And one anecdote that I can give you is that many years ago, I had an undergraduate whom I literally had to convince her to do research in my lab. And she's a very good student, but she just really hadn't done research ever before. And so I convinced her that this was something that was very useful. She happened to be an African-American student, and she went on to much better and brighter things. And after she graduated from Stony Brook Kuma or summa cum laude, I forgot exactly what, she went on to Stanford for graduate school and graduated from Stanford, and now is working at a company. So that's an example where, being able to start at the very beginning, being able to connect with individual faculty members at the very beginning, becomes very useful exercise to be able to get yourself on the road to. Now, the one thing that I also want to stress, and the very fact that you guys are actually attending this workshop that we're holding here this afternoon, at least shows to me that you're motivated. Okay, so I also am very much, very keen on the fact that it's not only the fact that you need to gain knowledge, but you also need to do it in a way in which you're clearly learning. So, and I think that, faculty recognize this. It's not simply a matter of building up your resume CV. You have to also have that other component in which you're truly motivated to learn, self-improve, to become better, greater, being able to get that knowledge base that makes you, a more educated and improved scientist and individual, so that at the end of the day, when it comes time for you to get a job, you become marketable, and you become marketable in a good way. And what I mean by that is, again, not only having the knowledge, but also having the commensurate level of motivation and maturity to know that, you're using it in a good way. You're using it because, you're doing it to, advance yourself, and not just some way of being able to pay the bills. I think that we, as faculty, recognize, and I guess are much more comfortable with students who are in our labs who really want to learn. I'll put it that way. I think that's really important. And again, the very fact that you're here today I like it, because that means that you want to learn.
And we have a follow-up question, which I think you sort of answered, about how to get involved. And is it, best to just send an email, or maybe go to office hours?
Right. So if I were you, again, this is it's a little different from when I was at your stage, but what one would do is to look at the website and look through the various web pages of the different faculty members, and find either science or, some sort of molecular, motivator that you believe is something that excites you, that interests you. There's folks who join me because they want to do sustainable chemistry, and they want to, for instance, they're interested in the way that my group wants to generate materials that at the end of the day will be the components of better batteries, better fuel cells, and better solar devices, which is another area which we work on, but I really haven't had time to talk about. So, and again, if you're interested in that sort of science, and you have, some good reason to, any reasonable faculty member will be very excited to talk to you. And I think that, again, there's some times in which there's not enough space in that faculty members group. And then, as long as you have other alternatives, choices that you can also go to, then that's actually very good as well. But the main point which I want to stress is that, you should have some plan and some idea, and it may be based on courses, may be based on your interests, and then look at, the faculty member's webpage, and maybe attend his or her class. And then, if you're in the person's class, go up to the faculty member at the very end, and have time to ask for an appointment, so that you can have more time to talk to him or her, or just email. And so being able to have that sort of interaction, and to have that sort of, don't be shy about it if you really want to learn. But again, be motivated, and at the same time, come to it from the perspective that sort of why you want to join this particular individual. And again, not so. Here's the thing, and I sometimes I find that. So, for instance, chemistry majors in our department need to have a research experience. It's part of being a chemistry major. But having someone email me in the spring semester of their senior year, it doesn't really make me happy, obviously, because it just tells me that this is just a box they want to check off, and they don't care about research. They don't care about anything. They just want to be able to fulfill a requirement. you need to be self-motivated enough, you need to plan for things enough so that there is something where, you can start at the very beginning. The sooner that you start, the earlier. And, I can say that when I was a freshman in college, that's what I did. I got involved in research at the very, very beginning. Actually, if I remember, I think by the time I graduated, I had actually worked in 4 different research labs by the time I graduated, just to get the experience of what it was to work in those different areas. And then, that was useful in my particular case. So I think that, if you are, again, want to be able to have a good feeling for what it is that you want to study, and again, chemistry underlies, it's good for graduate school, essential science, good for medical school, etc. But you want to be motivated enough to start early, and the earlier that you start, the better it's going to be. Okay.
Yes,
Hope that
that is
answers that
very
question.
valuable advice. That's fantastic. I don't see any additional questions. I think that we can, if we have any closing remarks, I will thank everyone definitely for joining us today. I hope you enjoyed today's presentation, and as I mentioned earlier, it will be available for you to review later this week on the Stony Brook Undergraduate Admissions YouTube page. Thank you so much, Stanislaus Wong, for joining us and presenting to our group, and have a wonderful rest of your day, everybody. Thank you.
Okay, thank you. Again,
Thank you.
any questions, just feel free to email us and we'll be pleased to answer them.